Hi everyone, let's talk about solving linear Diophantine equations. The Diophantine equations that we're going to be looking at are of the form ax plus by equals to c, where a and b, a is non-zero integer, b is a non-zero integer, and c is just any integer, and x and y are integer variables. So we want to find all x and y that satisfy this equation. And there are two questions we're going to have to ask ourselves. One, when a solution exists at all. Two, if a solution exists, find all of them. So let's tackle the first question. And if you're looking for a visualization, the way that I would think of it is that we have a line and we're looking for lattice points on that line. And they're going to be evenly spaced out, as we're going to see. By lattice points, I mean points on the Cartesian plane that have both coordinates are integers. So first of all, we're going to show for the first component that there exists a solution if and only if C is a multiple of GCD A and B. And we're going to derive this from Bézout's lemma. So first of all, let's look at the first direction, that there exists a solution. Let's call it xy. Then ax plus by equals to c, and GCD of a and b, it divides a, it divides b, so it divides ax plus by, which equals to c. So the first direction holds. Now for the second direction, suppose c is equal to k times GCD of a and b. And now we're going to pull in Bézout's lemma. By Bézout, there exists x and y in the integers such that ax plus by is equal to GCD of a and b. So all we have to do is multiply both sides by k, and we get a times kx plus b times ky is equal to c, because c is k times GCD of a and b. So we can choose kx and ky to be our solution. Okay, so next we're going to look at the second component over here, the second component of the theorem, which is characterizing all solutions based off of one solution. So let's make a little border here. Say x1, y1 is a solution. So we found one solution. And you can find the solution using the extended Euclidean algorithm. I've talked about this in a different video where we use the extended Euclidean algorithm to find one solution with the Bézout coefficients. So here's what's going to be true. x2, y2 is another solution. It could be the same solution, so it's just a solution if and only if there exists an integer k such that x2, y2 is equal to the following form: x1 minus k times b over the GCD of a and b. I'm just dropping the GCD here, comma, y1 plus k times a over GCD of a and b. And this is easiest to conceptualize when the GCD of a and b is trivial, meaning it's equal to 1. But this is the general solution, and now we're going to prove it. So first of all, let's tackle the easy direction, which is that the easy direction is that if x2, y2 is equal to this form, then ax2 plus by2 is equal to c, and that's easy to verify. So let me do that very quickly. We have a times x1 minus k times b over GCD of a and b, comma y1 plus k times a over GCD of a and b. Sorry, that's the wrong form. We're going to have a times this plus b times this. And you can see that there's going to be some cancellation. This is going to cancel out with this, and we're going to be left with ax1 plus by1, and that's just equal to c, since we're assuming that x1, y1 is a solution. Now we tackle the harder direction, for which we're going to need Gauss's divisibility lemma. Suppose x2, y2 is a solution. Then we know that ax1 plus by1 is equal to c, and we know that ax2 plus by2 is equal to c. So we're going to subtract them, and by subtracting them we get that ax1 minus x2 is equal to by2 minus y1, and then we're going to divide by the GCD of a and b, and you'll see why in just a second. We get a over GCD of a and b times x1 minus x2 is equal to b over GCD of a and b times y2 minus y1. Now this number here, a over GCD of a and b, it divides this whole thing, but it's co-prime to the first component, so by Gauss's divisibility lemma, y2 is equal to y1 plus k times a over GCD of a and b for some k that is an integer. Okay, so we already have the first component, and for the second component we find that by this equation over here, we divide both sides by this, so we get that x2 is equal to x1 minus b over a y2 minus y1, and that is equal to x1 minus k times b over GCD of a and b. You can quickly compute that. That won't be difficult. So this is a complete parametrization. This solves the linear Diophantine equation completely. Thanks for watching, and I'll see you next time.